Let's jump right in. Welcome to this explainer. Today, we're taking a structured, academic, deep dive into the fundamental properties and the environmental cycle of hydrogen sulfide. You probably know it best by its chemical formula, H2S. Whether you're reviewing this for a science module, brushing up on environmental studies, or just kind of geeking out on atmospheric chemistry, we're going to establish a crystal clear understanding of this really fascinating compound.
So here's our roadmap for today. We'll be tracing the complete journey of this chemical, starting with its identification and detection, moving on to natural sources and atmospheric sinks, and finally wrapping up with its effects on materials and biological impacts.
All right, let's get into Section 1, Identification and Detection, Understanding and Sensing H2S.
Okay, take a look at this number, 0.0002 parts per million. That right there is the standard background concentration of hydrogen sulfide in our atmosphere. In mathematical terms, this is an incredibly minute quantity. To put that into perspective for a second, imagine a million individual particles of air just floating around. Out of all of those, only a tiny, fractional trace would actually be hydrogen sulfide. It's a true trace gas. It exists in the ambient air around us at levels so incredibly low that they barely even register on standard atmospheric scales.
But you know what's truly fascinating? It's how that tiny background number contrasts with our own biology. Our olfactory system, our sense of smell, is so remarkably sensitive that we can detect its distinct odor even at these exceptionally small concentrations. You absolutely do not need a heavy, concentrated cloud of this gas to know it's there. Human bodies are naturally equipped with chemical sensors right in our noses that instantly recognize it. It really showcases this brilliant intersection between atmospheric chemistry and human anatomy.
Moving right along to Section 2, the cycle, sources and sinks.
So where does this gas actually come from? Well, as we can see here, it originates from three distinct natural mechanisms. First up, we've got the organic category, and this is driven by the anaerobic decomposition of organic matter. Remember, anaerobic simply means this breakdown happens completely without oxygen. Next, we have the mineral category, which involves the chemical reduction of sulfur found naturally tucked away within the Earth's mineral deposits. And finally, and honestly this is perhaps the most intriguing one, is the bacterial category. This involves a highly precise biological reduction of sulfate and organosulfur compounds by a specialized bacterium known as Desulfovibrio desulfuricans. It's quite a mouthful, I know, but this microscopic organism essentially acts as a tiny biological factory, actively contributing to the global sulfur cycle.
Now, here is the crucial point. It doesn't just build up in the air forever. The atmosphere actually acts as a natural sink where the gas is actively oxidized and safely cleared away. So despite all those organic, mineral, and bacterial sources constantly pumping H2S into our environment, natural chemical reactions with oxygen in the air continuously scrub it right out of the atmosphere. And it's exactly this delicate, ongoing process of oxidation that keeps the background concentration at that incredibly low 0.0002 parts per million we talked about earlier.
Let's look at Section 3, the impacts, interactions with materials and living organisms.
This targeted chemical reactivity is absolutely vital to understand. Notice how H2S uniquely degrades different materials. It physically blackens lead-based paints, but it merely tarnishes silver objects. If you look at the left side of our comparison, the reaction with lead is actually quite severe. It fundamentally alters the pigment, causing a really distinct, harsh blackening. Conversely, on the right side, when hydrogen sulfide interacts with silver ornaments or vessels, it just reacts with that surface layer. It creates a tarnish, which is just a dulling effect, completely chemically distinct from how it destroys the lead. This specific targeted reactivity is an essential concept for folks working in everything from material science to the preservation of historical artifacts.
Shifting gears to biological organisms, meaning us, plants, and animals, we are super fortunate that high levels of exposure just aren't common in standard environments. We can largely thank those highly efficient atmospheric sinks we just analyzed for that. However, we have to strictly respect the fact that this gas is fundamentally toxic to both plant and animal life. No exceptions. Because of this inherent danger, if you're in a confined space or in specific industrial situations where concentrations are allowed to rise, H2S becomes a severe biological hazard.
I want to leave you with this final thought to consider regarding our own biology. If we can detect it at such minute atmospheric levels, how effectively does our sense of smell protect us before toxic exposure actually occurs? Think about that. Beautifully complex relationship between the severe toxicity of the gas and our ability to detect it at mere fractions of a part per million. Is our incredible sensitivity to this smell a perfectly evolved early warning system against a highly toxic threat? It really forces us to appreciate the brilliant engineering of nature. Thank you so much for joining me for this explainer. I hope this structured academic breakdown has clarified the science of hydrogen sulfide for you. Keep analyzing the world around you, and I'll see you in the next explainer.